So in the last video, I was introducing you to the Punnett square and how we use the Punnett square in order to hypothesize what the children would be if we have certain individuals mating. So in our lab, we're going to use the example of heterozygotes mating many times. So I think this is a really important Punnett square to look at. So in the explanation of what Mendel did, I talked about the P generation, the parents who were both homozygous, one homozygous dominant, one recessive, and they mated and created all dominant phenotypes. But what they also created were all heterozygote genotypes. So then he allowed for those heterozygotes to self-pollinate. So that Punnett square would look like this, where you would have one of the gametes with a dominant allele and the other with the recessive for both parent 1 and parent 2. So take a second, if I were you, pause this and do this Punnett square. Practice it. Make sure you're feeling really comfortable with this so that we can talk more about how these are used. So now that you've done that, what are our possible offspring? Right, so your Punnett square should look like this, where you have brought down the top alleles and brought over the alleles from parent 2 on the right. So what we have phenotype-wise, right? So remember, phenotype is our dominant versus our recessives that we can actually see. So any individual with a big R here has the dominant allele, so they are going to have the dominant phenotype. The one who has the no dominance, that only has recessive alleles, will be our recessive phenotype, which means this is our 3-to-1 ratio that we mentioned earlier. This is also the ratio you'll be using for most of this lab. Now let's also talk about genotype, because it is important to think about that as well, even though that's not something we're going to be counting and really looking at in this lab, because we don't have the ability to test DNA in our lab. So genotype ratio is something that we can look at here as well. We know that one of these is homozygous dominant, right? One is big R, big R. Two of them are heterozygotes, big R, little r, and then the last one is a homozygous recessive genotype that is going to have the two little r's, which means our genotype ratio is a 1 to 2 to 1 ratio. So again, in the lab, we're going to be using phenotype because we're going to be counting, and we are using this monohybrid cross because we are only looking at one character. Now, there are two situations in the lab for the last two experiments where you are going to be looking at what's called a dihybrid cross. So a dihybrid cross is actually looking at two characters, so two different things. So in this example, in this picture, you are looking at yellow and green seeds, and you are looking at smooth versus wrinkled seeds. So that is two different things. You're looking at one, the color of the seed, and two is the texture of the seed. So when we look at these, we're looking at two totally different things. So in this example, we are looking at a purebred, homozygous dominant yellow smooth seed, which you can see in the picture as YYRR, right? So here's your YYRR. And then the other one is a purebred recessive with little y, little r, because it is green and wrinkled. So when those are bred together, we see the same phenomenon that we saw earlier in that all of the offspring are the same. They all look dominant. They're both yellow and smooth. But when we take these heterozygotes and breed them, that's when we get the interesting stuff that comes out. And this ratio is something that you should know. So this heterozygote cross gives us a 9 to 3 to 3 to 1 ratio. So again, this is phenotype. Genotype obviously is a little more complicated than that if you were to look at all of these, but phenotype, you can see that 9 of these are yellow and smooth, so that's our dominant phenotype. 3 of them are green and smooth, so that's one dominant and one recessive. And then there are also 3 that are dominant for the other of the traits we're looking, or the characters we're looking at, and recessive for the other. So we have 3 of them that are yellow and wrinkled here. And then you get 1 out of the 16 possibilities that will be recessive for both. That is our homozygous recessive individual. So that's where our 9 to 3 to 3 to 1 ratio comes from. This is the phenotype of a heterozygote cross. So the other thing we're going to be looking at in this lab is kind of taking these these Punnett squares, these hypotheses, which is really what a Punnett square is. It's a hypothesis of what children could result. And we are going to be testing to see if that is indeed what we get. So we need to talk a little bit about statistics and probability. So in this lab, in the lab book, you will see the equation for probability. We're going to break this down so that you can kind of solve it step by step to think about how probability then can be compared to what we actually see in the real world, right? What we're actually counting. So probability is kind of sort of like a percentage, right? The number of ways something can happen out of the total number of possibilities that are available. So in the lab, we're going to be using one of the easiest examples, which is flipping coins. All right, so what's the probability of flipping tails when you flip a coin? Well, there's one tail out of two options, right? So your probability is 1 out of 2. Or, of course, you can simplify that to 0.5 or 50%. So we can do this for just about anything, right? So another example you'll see in the lab a couple of times is about a rolling die. So if you roll a 6-sided die, right, what's the chance of rolling a 3? Right? So the way that this is written, right, you have the probability of rolling a 3. So there is 1 3 and there are 6 sides. So you have 1 3, 6 sides. So 1 out of 6. Your chance of rolling a 3 is 1 out of 6. So that can be simplified to 0.17 or 17%. So you can do this for, again, just about anything that we're going to be looking at. How many chances are there and how many total possible outcomes are there? So we're going to be applying this as we discuss this lab. So there are 4 rules of probability that you should be aware of. First rule, very important. Every event is independent of the one before it, which means if you're flipping a coin, if you flip heads the first time, the next time you flip the coin, heads is just as likely as it was the first time. So I think one of the funnest examples to look at are when you start talking about how families have babies and how many of them are males versus females, how many boys versus girls. If a family has 3 boys and mom is pregnant again, and what's the chance of that 4th kid also being a boy? Now the reality is that boy is independent of all the others, right? That baby is independent of all of the rest of the children, which means it's still a 50-50 chance of being a boy versus a girl. Now this is a very different question than what's the chance of a family having 4 boys in a row. That's a very different story. We'll actually come up to that rule in a second. So the second rule I find really, like, this is common sense. The sum of all the things in the thing is 100%. The sum of all the outcomes must equal 1 or 100%. So if we are talking about the probability of a boy and a girl, right, the probability of having a boy is 1 out of 2. The probability of having a girl is 1 out of 2. So if you add 0.5 and 0.5 together, you would get 1. Same thing with a die, right? If you rolled a die, the chance of getting a 1 is 1 out of 6. 2 is 1 out of 6, 3 is 1 out of 6. They're all 1 out of 6 and there's 6 of them. So if you add 1 out of 6 together 6 times, it equals 1. This is a really great way for you to double check your math as you're going through this lab. So the next 2 rules are both mathematical. We can use these to actually determine what the chance of something happening, what's the probability of something happening. So rule number 3 is called the addition rule. Basically, if you want to know what's the chance of one thing happening or another thing happening, we can add those together. So this, again, the simplest example here is what's the chance of having a boy or a girl? I mean, basically the question is here, what's the chance of having a baby? The chance of having a baby is 100%. Now you could also do this with rolling the die, right? What's the chance of rolling a 1 or a 2? Well, the chance of rolling a 1 is 1 out of 6, and you would add that to the chance of rolling a 2, which is also 1 out of 6. So 1 out of 6 plus 1 out of 6 would be 2 out of 6. Or you could simplify that to 1 out of 3. So if you ever see the word or inside a question, that is an addition question, right? What's the chance of rolling a 1 or a 5? That is addition. Now that's different than if we want to know what's the chance of something happening one after the other or happening at the same time, which is what rule number 4 is. So rule number 4 is called the multiplication rule. Basically, what's the chance of two things happening at the same time or back to back in some situations? All right, so the example, what's the chance of having a boy followed by a boy? Okay, so if you're having a baby, what's the chance of having two boys in a row? Well, the chance of having one boy is still 50%, and the second boy is still 50%. But if you want to know what the chance of having two in a row is, you have to multiply them together. So if you ever see something that says at the same time or an and in the question, you're going to be multiplying that because you want to know what the chance is of having both of them. And that is going to compound. So the chance of having a boy, 0.5, times another boy, 0.5, gives us 0.25. So practice, what's the chance of having four boys in a row? Right? So again, we're talking about things that are happening at the same time or in order. What's the chance of having four boys in a row? You would have to do 0.5 times 0.5 times 0.5 times 0.5 to get your answer, right? What's the chance of these things happening in a row? So as we apply this to our lab, you are going to first start by flipping some coins. So procedure 10.1 is you collecting some data. You're going to collect data the simplest kind possible by flipping coins. Now you know the chance of flipping heads is 50% and tails is 50%. But what we need to know is that what you actually get, and is that an accurate percentage? So we know the probability of this is heads, tails, 50% to 50%. But what do you actually get in the field, and how does that compare? That's really what we're focusing on in this lab.